This Week in Radio Tech, episode 231, is brought to you by the Axia Element 2.0 IP audio console, protected by an industry-leading 5-year warranty. By Lavo, maker of the new Crystal Clear virtual radio console. Crystal Clear is the radio console with a multi-touch touchscreen interface. And by the Telos Zip 1 IP codec, the IP codec that drops JAWS, not audio. Hey, Ward Silver is a teacher, a contributing editor to the American Radio Relay League, and the author of the book Ham Radio for Dummies, as well as other books. We're getting a lesson from Ward on quadrature amplitude modulation, as well as I and Q signals. Symbol constellations, predictive coding, we are diving right in. Join us. Hey, welcome into This Week in Radio Tech. Yes, it's time to talk about radio technology, and that is everything from the microphone to the light bulb at the top of the tower, and now just so many more things that may not even involve the tower. I'm Kirk Harnack, your host. This is episode number 231. And we're glad to have you along. Be sure you tell your friends and engineering neighbors about This Week in Radio Tech. You can watch it live on the GFQ network, as you may be watching it now. You can also download the show. You can download the audio. You can subscribe to the download with your favorite pod-catching device, service, software. And you can also watch the show at the gfqnetwork.com website or at thisweekinradiotech.com. And several other services, too. You can watch the show. Just Google it, This Week in Radio Tech. I'm sure you'll find it. Hey, on the show today, we have one of our reliable co-hosts, the best-dressed engineer in radio, reporting from Manhattan. Ladies and gentlemen, it's Chris Tobin. Hey, Chris, welcome in.
Hello, Kirk. Yes, I'm in Manhattan. I'm at a home business operation, a friend of mine doing some engineering stuff. So I thought I'd quickly get out onto the balcony and set up a light kit and a camera and go for it. So far, it's working.
Hey, what kind of light kit are you using there? Is it a real light kit, or is it, the floor lamp from the house?
It is a CFL flood lamp that I purchased at a local lighting store. The color temperature is 5,000 Kelvin, and it works just right with this webcam. And I've been using it for all the live shots.
What do the neighbors think? Does it bother neighbors? Is it that bright?
No. It's focused.
Okay.
No, it's not like a typical TV stand-up that I'm accustomed to doing with other folks, being behind the camera. And no, this is definitely very subtle.
Cool. Hey, our guest on the show, I'm really excited to have this gentleman on because I didn't know our guest's name until maybe a couple of months ago. And I'm reading through the latest QST magazine that crossed my desk. And in fact, I'm probably eating my cereal in the morning, looking through QST magazine. And there's an article about digital transmission and how digital transmission actually works with RF to get information from here to there. And this is something that, we deal with, but I don't really know exactly how this stuff works. And our guest is Ward Silver. Ward is a call sign November 0 Alpha X-ray, N0AX. Ward, welcome in to This Week in Radio Tech. We're glad you're here.
Hi, I'm glad to be here, and I'm happy that you read the article in QST, and it seemed to certainly hit a chord. So on with the show.
It sure did, and I looked you up on the internet and found your email and somehow got in touch with you. Thanks for responding, and thanks for agreeing to be on our show. This is a show where we have fun, we talk amongst engineers, we tell stories, but if we can have a lot of teachable moments, that's what we're really after. We want to teach other engineers what the experts know about various subjects. So we've had shows on the rigors of amplitude modulation and frequency modulation, studio techniques, how-to shows on how to maintain this or that. We had a show where I took a video camera in and it showed how we change a blower motor on a 10 kilowatt FM transmitter. So there's just all kinds of things that we do shows on, and we've had guests from every walk of life. You may be familiar with the C. Crane Company, Bob Crane, who makes those consumer radios that are so popular. We just had Bob on a couple weeks ago. So glad to have you on and talk to us about this digital mode. By the way, I want to mention Ward, I'm sure will show us, well, maybe you can pop it up now. Ward, you're the author of a book that ought to be instant Christmas wish list right here. If you've got somebody in your life who's technical.
Yeah. Ham Radio for Dummies.
Ham Radio for Dummies. And
second edition.
I don't know that any ham radio guy would be insulted to be called a dummy if he got a book called Ham Radio for Dummies. I certainly wouldn't be.
Everybody's a dummy. Everybody's a dummy about something, and it's such a big hobby anymore that nobody. It used to be you could read this little magazine. It was this big. It was about that thick, and if you read the whole thing, you could tell everything there was to know about ham radio that month. But now it's just so broad, so deep. Nobody knows everything about it all.
You're exactly right. I a few years ago I thought ham radio was kind of dying out, and yet I look at the membership numbers and it is not dying out. There are ham radio operators around the world. It's just getting more popular, and all the new all new, they've been around for a while. All these modes that we have, ham radio doesn't necessarily mean one thing. I'm getting ahead of myself. Let's hit up one of our sponsors for some money right now. Our show is brought to you by three sponsors: the folks at Axia, also the folks at Telos, and at Lavo. And our first sponsor on this show is going to be from Axia. Now, I'm really familiar with Axia because it's part of the company that's called the Telos Alliance, and they're my employer. So I want to thank them, first of all, for sponsoring This Week in Radio Tech. And we want to tell you a little bit about the console, the audio console that is the real flagship of the Axia lineup. You go to so many broadcasters around the world, and it's close to 5,000 studios now that have an Axia Element console in them. This is the big workhorse. I'm not sure if Andrew's going to find a picture to throw up on there, but the Axia Element console, it's not just, if you look at one, you've seen one, but you know what? You can order this console in literally about 14,000 different iterations. It's variable in size. You can choose the size of frame you want. You can have a double frame if you like, even 4 frames if you like. You can put any number of faders in there that you want, from 2 faders up to 40 faders. You can have a 40 fader console if you like. There are accessory modules that can go into the console. So if you want a telephone controller to control your phone system, bam, just put it right there in the console. It is right there available for the operator to use quickly and easily. Intercom buttons, so you can quickly intercom to any other intercom station around your facility. Even the soft intercoms, that is an intercom that's just running on a PC. You can have hard buttons that we call film cap buttons. You can have soft or smart switches that have a text label that can be changed on that. They can change instant by instant if you wanted to. So many options, so many ways to order the console. You can spend a day just figuring out what options you want to go in one of these Axia Element consoles. Now, I've installed a bunch of these all around the world, especially at trade shows, if you want to count those. But, we do build real radio stations at trade shows, or real studios anyway. The Axia Element console connects to either the Axia Power Station, and that's a big honking piece of gear that goes in the rack. It's got the power supply for the console, the power supply for the DSP engine, the mixing engine. It also powers the audio input and output that's built into the back of the power station, and it powers the Ethernet switch, the gigabit Ethernet switch that's built into the back of the power station. So you put the Axia Element console and all its different permutations, the ways you can order it, match that with an Axia Power Station, you have got a rock-solid audio console for any audio studio, any radio, even television. These are being used in television stations actually in different countries as well as here in the U.S. I've seen some of them. So check it out on the web if you would. I'm so excited about this console. You can't go wrong because there are thousands of them on the air right now. The Axia Element console. Go to axiaaudio.com and look for Element 2.0 console system is what you'll find it under. And thanks to Axia for sponsoring This Week in Radio Tech. Remember, you can't go wrong, and Axia connects to so many other brands and systems using audio over IP on Livewire. All right. Hey, we're on episode 231 of This Week in Radio Tech. Chris Tobin, the best-dressed engineer in radio, is with us, and our guest is Ward. There he is. Our guest is Ward Silver. And so let's jump right into it. And Chris, you might want to get ready with some follow-up questions here. Ward, digital transmission. I want to understand this. Where would you start me out in understanding how we can transmit stuff that recovers as digital ones and zeros as opposed to amplitude modulation, frequency modulation, single sideband modulation, phase modulation. How do we get ones and zeros onto this analog carrier and make it come out the other end? Where do you start me out at?
Okay, well, let's see. When I was a datacom engineer, I used to have a little card that I kept in my pocket all the time that I'd take out and I'd say, well, it depends. That's what was on the card. To any possible question that somebody would come up and ask. When I talk to people that are experienced with RF, and I used to be a broadcast engineer. I spent 8 years in broadcasting back in the 70s and early 80s in FM and AM and even television. And I watched for interesting shows, technical shows about how to get a giant tube with two handles out of a finger stock with using a engine hoist or something like that.
Yes.
That was high tech back then. Anyway, back in the day, it was AM and it was FM, and on the ham stations, you had single sideband. So that was it. It was analog modulation, and you would take an oscillator and you would mess with its output in some predictable way so that you wound up with something you could unmess with on the other end and recover a single channel of information as an analog waveform. Okay, the only digital data back then was radio teletype, and then we had some limited teletype over radio modes like AmTOR and GTOR, and that was typical of the commercial systems as well. So things progress, and in the late 1970s, 1979, 1980, the FCC decided to allow amateurs to use codes and like ASCII. That was a standard encoding mechanism for data, and suddenly amateurs were off to the races using the same sophisticated protocols that the commercial and the military guys were using, and we came up with an adaptation of the X.25 standard that became AX.25 for amateur X.25 and packet radio. And packet radio then spawned all sorts of interesting bulletin board systems, and there was a lot of overlap between the amateur world and the commercial wireless data group. For example, deep inside your CDMA phone is a media access control protocol called MACA, M-A-C-A, for multiple access carrier collision avoidance, multiple access collision avoidance. That was originally developed for packet radio and amateurs, but wound up becoming part of Wi-Fi and CDMA and other things because the same guys were working in both areas. Okay, so we have transmitters, we have audio, and we have this code. And then in the early 90s, another step was taken. Well, you can invent your own mode and use it as long as you publish the details of it so somebody else can use it. And so that sort of blew the doors wide off, and now there's dozens of digital modes that are being used in amateur radio, some of which leak over into commercial, and a lot of the commercial stuff has leaked over into amateur. So there's a lot of confusion on the part of amateurs trying to understand digital, just like broadcast engineers are starting to try and understand digital. And so how do you do this? How does it actually work? And you can get very technical very quickly. It's a very technical field with a lot of layers. You may have heard the term OSI 7-layer model, where it talks about all the different steps in this process that you go from your application music player or your email program, and then that transfers data here, and then there's another layer and another layer, and at some point things fly out over a wire or a transmitter, and then they bubble back up through another layer on the other side until they come out your headphones or show up on your computer screen. And if we jumped into it at that level of complexity, it would take several shows to deal with. So it's also a big drink of water for anybody who's just trying to get started. So the way I present it is let's talk about a pipe. And basically, we have three sections of this pipe. One is the actual pipe, and that's if you tuned a radio across a signal and you listen to it, you would hear what's going in across the pipe, and that's called the air link, AIR, the air link. That's what's actually being transmitted, and you might hear tones, you might hear this modem sound that it sounds like, and that's a phase shift modulation. You may hear lots of different things, but all those are carrying an encoded data as some kind of modification of a signal's frequency or phase or amplitude. Okay, the pipe connects on each end to these little machines. They're called protocols. And the protocols manage how the data gets into and out of the pipe and how the data is packaged so that the corresponding machine on the other end can look at what's coming out of its pipe and make sense out of it. And so the protocol's job is to translate what's going on in the air link down here at the bottom, or the physical layer, up to what's happening at the top, which is your music player or your email program, for two particular examples. And so they're basically taking data, and then they package it up and they stuff it into the pipe, and a modulator in the pipe turns it into an RF signal that goes out over the air. And the same process goes the other way on the other side. A demodulator receives the signal, it translates the characteristics of signal into ones and zeros. That it hands up to the protocol in the middle, says, here's ones and zeros, protocol, figure it out. And the protocol looks at the sequence of ones and zeros, turns it into characters and unpackages them, and then hands them farther up to whatever program is running up at the top. And it might be an MP3 file, it might be an audio stream, it might be a binary file, like I'm sending a file back and forth, or it might be an email. It might be anything. The protocol really doesn't care. It just wants data, and it handles the data going in and out of the pipe. So you've got three levels. You've got the pipe down at the bottom, that's your air link. You can listen to it with a radio. You've got your protocol, which is a little machine for getting data in and out of the pipe in a predictable and reliable way. And then up at the top, you've got your application, which is whatever program that you're trying to send or receive data from. And that's basically the structure in which you can start to understand these things. And depending on where your interests are, either professional or personal, you can focus at any level of that three-level stack. And if you're interested in the RF part of it, you stay with the pipe. If you're a protocol guy, then you stay with the little machines. And maybe you're a user, so you stay up at the top level. And that's basically how I approach the problem. So how about if I be quiet for a minute and we'll let her react to that.
I've got to chew on that for just a minute. Hey, Chris Tobin, you and I have had a number of conversations over the years about your use of various digital pieces of equipment. I think you've even used transmitters and receivers intended for television work, ENG work, to transmit digital audio from here to there. Tell me about how you got interested in that, and relate what you can about how they work to this discussion about how this modulation takes place.
Oh, gee, that's a good one.
Well, I think the letters COFDM or COFDM.
Yeah, I'm trying to think of the best way to put it, because when I was playing with the COFDM and various other versions of the TDMA, CDMA that's out there, the TV guys I was working with, we did some video links in Washington, D.C., and we were learning and discovering, and same thing with Moto Turbo, which is a land mobile version of a digital format. And we discovered that the less direct line of sight you had with the transmitter to the receiver, the more robust the signal was for recovering.
And that's pretty counterintuitive. That's what COFDM does for you.
That's what got everybody confused. So the group of us, which were amateur operators and broadcast engineers, and we're all sitting there on the mall in Washington, going, okay, let me get this straight. I'm now pointing the antenna at a building, and you're receiving the signal, and it's, we'll just say, full DFQ, full quieting, pure video, everything is what it's supposed to be. Now, when I point it toward you at the building you're in with the antenna on in the window, you're having macro blocking and dropouts, and it just doesn't work. And they're like, yes, this is about 5-6 years ago. So we're like, wow, this is really interesting. And as we move forward to today, and over the last couple of years, I've been using the same technology for radio and doing all kinds of audio stuff. And now it's like becoming, commonplace. Your Wi-Fi is a form of the OFDM, thinking.
Oh, Wi-Fi is Wi-Fi is probably a good example, because broadcast engineers, we certainly touch that quite a bit. We also touch the modulation techniques used in HD radio. And Ward, I recall a conversation I had some years ago with an engineer who was working on the Ubiquity HD radio system, and he was telling me about advances that they had made in, I want to say the figure of merit, or the term he was using was bits per hertz. So the number of bits you could get per hertz of bandwidth, perhaps it was. Can you help me understand that concept of counting or getting efficient with bits for a given bandwidth?
There's a fundamental rule. It's called Shannon's law. It says you can get X number of bits in a bandwidth of a certain width in hertz, and as I recall, that's it takes 2 hertz to get 1 bit per second through it, or something like that. It's a 2-to-1 relationship, and each bit that you send through, it could just be a 0 or a 1. If you don't know anything about the signal and you're just listening for 0 or 1, imagine yourself looking at a guy with a semaphore flag far away through binoculars, and you want to know whether he's waving the flag or he's not waving the flag. That's a 0 or 1, and basically that's what you're doing in a raw data environment. You're listening. Your pipeline is listening for that 0 or 1 coming through. And if you have a very simple encoding and protocol, that's basically your limit. Well, that puts some pretty severe limits on how much data you can get through this pipe. So by using more and more sophisticated codes in the presence of noise and all the other horrible things that happen to an RF signal as they go along, you can get closer and closer and closer to the theoretical maximum. But what you do is you add error correction information, you add predictive coding, you do all sorts of interesting things to make the data transmission process more robust. Each type of signal, like HDTV or HD radio or anything else, has its own method of encoding and packing data and assembling it so that it's transmitted with the most bits per unit of bandwidth, yet still preserves some required limit of fidelity and resistance to errors. It's like Chris was talking about, the idea that he would have a full quieting, very strong signal at the other end, but it would still break up and pixelate and just basically be unusable, probably because of some kind of multipath where you have 2 very strong paths coming from the transmitter and then coming back to the receiver with a slight phase difference between them, so that they interfere. Even though the signals might be very strong, they're interfering with each other, and that distorts the signal so badly that the encoding can't recover from it. So by pointing the antenna off in some other direction, you find a way of getting the signal from here to there by only one path, where there's not some competing path that's trying to interfere with it. And even though that's counterintuitive, what the receiver hears is only one clean signal, even if it goes by another path. And so that's a little bit off the subject, but basically by improving the robustness and the fidelity of the signal, you can use more and more sophisticated codes to help recover from the distortions and fadings and all the other things, noise, that the signal encounters on its way. And each time you have a signaling event, each time the guy with the flag waves it or doesn't waves it, that's called a symbol. And the number of symbols that you can pump through your protocol and pipe tell you how much data you can pack into the bandwidth of the signal. The symbols are what the coding machine produces, and you wind up with, I have a copy of that article that you were talking about here, and you can see
that's
this,
it. Yes, yes.
this little diagram. There we go. I'm running back. Okay. And all right, we'll get it that way. That particular coding has 4 different states. Each one of the corners here, this one and this one and this one and this one. I would not make a very good weatherman. I'm not doing this very well. But what it can send is 4 different symbols through the pipe. This one and this one and this one and this one. And so the guy with the semaphore flag can wave his flag 4 different ways. And the system at the other end tries to detect which one of those symbols has come through the pipe. And the lines on this drawing here show the machine at the other end trying to decide which one of those signals has come through. And any kind of noise or distortion shows up as the variations in those lines as it moves around this diagram. So if I sent you a sequence of these 4 symbols, that's basically a drawing showing how the machine on the other end is trying to recover each one of those symbols. And then if I can make each of those symbols apply to more than 1 digital bit at a time, then I can send more bits per symbol than just 1. When you hear a modem, we all remember the old training sequence where the modem starts out with a couple of tones, and then it has another couple of tones, and then there's this back and forth between the 2 modems, and then it goes like that.
Yes.
That's a training sequence, and basically the 2 modems are talking to each other saying, can you do 1 bit per symbol? And the other one says, yeah, I can do 1 bit per symbol. Yeah, so the first one says, how about 2 bits per symbol? Okay, I can do 2. How about 4? Can you do 4? And then it says, yeah, I can do 4. Okay, so and they build up that way until one of them says, no, I can't go any farther. So they settle at this particular set of encoding and the number of bits per symbol, and then they agree on that, and then they start exchanging data back and forth. So for a particular channel and a particular type of modulation, there are limits about how many bits you can pack in per symbol. And the modems or the systems on each end, the protocol engines, will negotiate back and forth to see how many bits that is, and then they'll apply the appropriate coding. So the number of bits per hertz is not fixed, although for broadcast, where you don't have a negotiation between the receiver, which just receives, and the transmitter, which just transmits, you only have basically 1 symbol rate and a fixed number of bits per symbol. But when you're talking about a communication system going back and forth where both have intelligence, you can negotiate the number of bits per symbol. And the number of bits per symbol then ultimately determines your bit rate and whether you got enough bandwidth there with all the other, what am I trying to say here? With all the other constraints that you've placed on the system. If you have a certain level of error rate that you can tolerate, then the system will tell you, I can get, say, full CD quality 44.1 kbits per second audio, or maybe I'm doing 192 kilobyte per second digitization or something like that. based on their ability to negotiate between each end of the link. But in broadcast, where you're just shoving data into a transmitter, out it goes, and the receivers are never communicate with the transmitter. You basically have to pick one symbol rate and stay with it. So in that case, the broadcast industry has done modeling to say, within our expected coverage area and the expected quality of receiver, what is our expected maximum symbol rate, and we're going to stick with that. That'll satisfy, say, 90 or 95% of our expected customers, and that's how it works. I'm going to stop again and let you get a word in edgewise there, Kirk. Go ahead.
Well, I'm sure Chris Tobin would have a comment or a question, but I got a quick one. And well, actually, it's a quick question. The answer may not be quick. I want to understand generally this rule or this axiom, or what is the relationship between efficiency and robustness in a digital system? I've been led to believe that if you did some kind of modulation that's, say, 64 QAM or 128 QAM, that's a whole bunch of possible symbol locations, but that system itself is kind of fragile. It becomes very difficult to determine is my signal ending up here or here or here. And maybe we should explain a bit about what QAM is, Quadrature Amplitude Modulation, and is just what that means. But I'm curious to understand this relationship between efficiency and robustness.
Okay. All right. I'll make this a very quick answer. I'm going to go back to this diagram here. This is called a constellation diagram, and each one of the 4 points are the points of the constellation, and there are 4. And so this might be quadrature amplitude modulation, it might be quadrature phase shift modulation, but basically the system moves around between those 4 points. That's all you get, 4 different symbols. And you can see from this diagram what happens when there's noise or distortion in the error. The errors start to build up, and it's harder for the system to determine whether the system is here at say at this point, right here in the corner, or is it down here, or is it over here? It's hard to tell, and the faster you move, the harder it is to decide. So some of these systems, they don't have 4 states, they might have 16. There are systems that use up to 256 different points in the constellation, and there's even more, but I think the biggest one that you'll encounter commercially is 256 states in the constellation. And so the machine on the other end has to decide which of those 256 different states the data link is in. And if you have noise or distortion, or you're moving very fast, all 3 of those things make it harder to decide at the other end. And if it's harder to decide, you're more susceptible to error. So you have to balance speed and against ability to decide. So it's, do you want to be fast or do you want to be error free? And so you basically study your communication link, and you decide on a combination of speed and error rate that you can live with, and then you stay with it. So the more different states you have, or the faster you move between them, the less robust your system is. Does that answer your question?
Yeah, I guess it does. It follows along with what I was thinking about it, and I guess before we get through our conversation, I want to also see if I can understand. I've read about the things we just talked about, QAM and 4 and 16, and as you mentioned, up to 256 or even higher, and I kind of understand that. Where the RF carrier is at a certain amplitude and in a certain phase at a certain time, and that represents a symbol. I would then like to see, okay, so what are there other forms of digital modulation besides what I understand as QAM? And you mentioned quadrature phase modulation, I believe. Are there other things as well? Are there other ways to modulate a carrier to convey digital information besides my little understanding of QAM?
I would say the big two are amplitude modulation and phase shift modulation, and combinations of the two. And they are picked for their various either economic considerations. Quadrature amplitude modulation is fairly inexpensive, both to generate and to receive. And then the more sophisticated types of modulation are, they cost more, but they're more tolerant of errors in the pipe. And so depending on your application, you pick certain types of modulation. And then beyond that, there are certain characteristics of the way that you move from symbol to symbol, such as shaping the pulses. There's different types of ways that you change between the different states that make it more robust when you're moving very fast. All those things add complexity, and they're all more expensive. So it's a budgeting kind of thing. I would say back in the old days, you just had a frequency shift keying where you had your two tones and the signal would jump back and forth between one tone or another. Radio teletype worked that way, and you could send that kind of signal through the voice voice input to a transmitter. But now, by having the two carriers, basically they're called I and Q, and one is in phase and one is 90 degrees out of phase. And so basically for quadrature amplitude modulation, you're turning them on and off. And so you have the 0, 0 state, you have the 1, 0 state, you have the 0, 1 state, and you have the 1, 1 state. So there are your four symbols. And so basically the system is just going like this and turning them on or off and moving around in that 4-point diagram. That's the simplest way to think of it. You can also do that with phase shift, and you can also do it with combinations of things. So as you can see, it gets really complicated really quick. Back to you.
Hey, Chris Tobin, I've got a question, but I think it's going to be a long answer. So tell you what, Chris, have you got a question you'd like to pass along or comment on right now?
Well, the only thing I'll comment on, I have no question at the moment because the answers have been made clear, is that the Shannon's law, which came out in the 40s, he's a Bell Labs engineer, was based on work done by Nyquist and Hartley back in the 20s. So to give you an idea of the history that we're talking about. So here is technology we're using today, digital, to do all kinds of great stuff that was developed and thought of, and somewhat ahead of its time. And it was done back in the 20s and the 40s because back in that time, the phone company was trying to find a better way to communicate over wire, over copper. And that's what these guys came up with. So that's the background I wanted to throw in there just for a little historical moment. And as far as the quadrature and trying to figure out what, which quam and phase shift, I think of it as like three-dimensional chess. Or if you're a Doctor Who fan, it's the TARDIS. It's basically you're playing with time, space, relationship, and everything else. And it's just, you have 90 degrees out of phase, 180, depends where it's at, and all these other things. And it just gets really wild when you start trying to figure out, as we were saying, the link budget and figure out what's more robust, what's more efficient, what's more economical. It's just fascinating when you start getting into it.
I do have some follow-up questions about quadrature and I and Q, and I maybe it's just my mental block, but this is something that I need a little bit more explanation on. And then after I get that clear, we're going to let Ward loose on whatever he wants to teach us. Hey, our show is brought to you. Our show is This Week in Radio Tech, by the way. It's episode number 231. Our guest is Ward Silver. Ward is the author of Ham Radio for Dummies, and he's a contributing editor at the ARRL, so you'll see his articles in QST Magazine and other ARRL publications. Our show is brought to you in part by the folks at Lavo. Lavo is a console manufacturer from Germany, and they have some absolutely gorgeous consoles. Usually, people think of Lavo as being really large consoles, and they certainly make those. But they also make smaller consoles that are appropriate for radio stations. And one of them that people are really talking about is the Crystal Clear. They're calling it the virtual radio mixing console because there isn't a hardware console in front of you. It is a multi-touch touchscreen provided by a high-speed computer running Windows 8, and the application just takes over, fills up the whole screen, Your talent, your disc jockeys never see windows. What they do see is an absolutely gorgeous audio console. Virtually, it's on their screen. And because the console is defined in software, that means that buttons can do fabulous things. You can touch a button and have it open up totally contextual options that are related only to what you're doing now, at that point with that fader. So what that means is if you've got a microphone fader and you touch the options button with this, you can do things that you don't have to be given a whole menu of stuff that's not related. You're just given the options that are available and appropriate for that fader in that use at that time. It is multi-touch, and that means you can move several faders up and down at the same time. You can turn faders on and off, touch option buttons, have your hand on the monitor fader so you can adjust your headphone settings or your speaker settings at the same time. Work with your on-air faders. So the console consists of two parts. One part goes in the rack, and that's where all your audio input and output goes. There's mic inputs, analog inputs, AES digital inputs, as well as outputs too, analog and AES digital outputs. There's also the option for audio over IP, and it follows the Ravenna standard. And the Ravenna standard for AOIP includes the newly, about 1 year now, approved AES 67 AOIP standard. So that's something that you may be very interested in for connecting studios together. The console, the other part of the console is the part that's in front of you, the operator. And that's this multi-touch touchscreen interface. Up to 10 touches at once. It'll totally follow all of them. And that's how you work the console. It's just that easy. The console features precision stereo PPM meters, integrated pre-fader level, or Q as we call it in the States, 3 stereo mixing groups, program 1, program 2, and a record mixing group. And there's even a panic button that can clear changes you've made to a current scene. So if you accidentally, whoops, oh, I didn't mean to do that, you push the button they call the panic button, and you're back to normal operation. It deletes whatever it is you just changed. It's like an undo button. 24 sources can come into the mix engine. 8 can be simultaneously active in your mixing platform on your console, because it's an 8-fader mixer. Power supply redundancy is available, and of course it has GPIO for on-air lamps and muting speakers. If you would check it out, you'd be very interested in this at the Lavo website. Lavo, L-A-W-O, it's pronounced Lavo, but we spell it L-A-W-O.com. Look for the radio consoles, and you'll find the crystal clear console. And thanks to Lavo for sponsoring part of This Week in Radio Tech. It's episode 231. Ward Silver is our guest, and our co-host, Chris Tobin, is along with us. Chris is live in Manhattan on a lovely evening there. Just gorgeous outside. Looks like a great night to have dinner out on the sidewalk instead of inside the restaurant.
Yeah. On my way in there, I can see from here, looking down onto the street, onto the avenue. There's 2 restaurants that have outdoor seating, and they're very busy. And actually, it's very comfortable. This spring-like weather today has been it's gorgeous, and it's clear skies. It's great.
I wish I could tell you I'd be right over, but can't do that. Our guest is Ward Silver. Now, Ward, okay, at least twice in our conversation, once before the show and once during the show, you have mentioned quadrature, and you've mentioned these letters I and Q. I almost feel like Sesame Street. Today's show about quadrature is brought to you by the letters I and Q. And Ward, I totally understand a carrier. I understand amplitude modulation and how it creates sidebands when you do that. I totally get frequency modulation. You move the carrier up and down, you get theoretically an infinite number of sidebands up and down. What I don't get is this I and Q and what those special about 90 degrees in relation to these carriers. Help me understand this concept.
Okay. You understand the basic single carrier analog modulation for amplitude modulation. The simplest is Morse code. You're just turning it on and off. Amplitude modulation, where you take a single carrier and you vary its amplitude to carry the signal. You can also have frequency modulation, where you have a single carrier and you move its frequency back and forth. IQ, or quadrature modulation, uses 2 carriers. It takes 1 carrier and it splits it into 2 paths. One where there's no phase shift, 0, and that's the in phase carrier or component, and the other is shifted 90 degrees. And so that is called the quadrature, 90 degrees. And the reason 90 degrees is special is because mathematically the two sinusoids, the two sine waves that are coming out, if one is 90 degrees shifted from the other, mathematically they're called orthogonal. And so they're easy to separate in a demodulator, for example. So if I take these two components, one in phase and one out of phase, and I shoot them through the pipe, it's easy for me to recover the two signals at the other end with a simple mixing circuit or a mixing algorithm if I'm using a software-defined radio or DSP, digital signal processing, and I can get two completely independent streams of data back out of the system. So the in phase gets modulated with ones and zeros, and the quadrature gets modulated with ones and zeros. They get combined in the transmitter. Off they go. They come out to the other end. I mix them down, or I apply my mathematics in the microprocessor, and I get out my ones and zeros on either side. So basically, by using this 90-degree phase shift and certain mathematical properties of the sinusoids, I basically have a much more robust way of looking at the information coming than if I only have one carrier and I'm only varying the amplitude up and down or the frequency back and forth.
I think I'm starting to get, at least I'm starting to get a little bit of an idea here. There's one thing that I'm still fuzzy on. What the I and the Q signals themselves, are they signals that are turning on and off? Are they going up and down in frequency? What am I looking for as a characteristic of what they are doing?
What they are doing, let's talk about quadrature amplitude modulation first. Quadrature from having the two different signals, the in phase and the Q, and I turn them on and I turn them off, so they can either be a 0 or a 1, and those are the four points of this diagram right there. Okay, for example, this right over here in this corner might be both I and Q off, 0. The 0 applied to both of them, and this one on the other side of the square, it's hard to move this back and forth, might be both of them on, or 1 1, and in this case one of them is off, and in this case the other one is off. So basically just the simplest IQ modulation there is QAM, and I'm just turning these signals on and off, and at the other end I get back my ones and zeros just from watching the two components turn on and off. I can also do that with phase. I can do a wide variety of things with those two signals, but the simplest one is quadrature amplitude modulation, where I'm simply turning the two components on and off.
If I were to really understand and learn about the I and the Q signals and the balance modulators and the 90-degree phase shift, if I really got that concept down, what's the next thing I need to move to? In other words, are there other forms of encoding transmission that are also popular? Or if I learn this really covers a lot of technology?
I would stay simple, start with QAM. The next thing you need to worry about is, okay, what kinds of coding and error detection and error correction can I apply to this data stream to increase the quality of the data I get out at the other end? And I wanted, while you were on the commercial break, I looked up the exact form of the of Shannon-Hartley information theorem, and it's in this handbook, the ARRL handbook that I edit, and it's in the form of an equation where the capacity of the channel is equal to the bandwidth that you have times the log base 2, not base 10, of 1 plus the signal to noise ratio, and that's in bits per second. So it depends on your bandwidth and it depends on the signal to noise ratio. And then you can also you can see this little graph up here.
Oh, yeah.
As the signal to noise ratio gets better and better and better, you can get closer and closer and closer to the theoretical maximum. So how do you make the signal to noise ratio better? Well, you can make your transmitter stronger. You can turn up the juice. Okay, that works. And that's a perfectly legitimate way of increasing your signal to noise ratio. Well, you can also do that in what's called coding space. And say, if I knew that there was only a certain sequence in that constellation diagram, if I knew I was down at this corner and I was always going to go this way, for example, it would make it a lot easier for me if I knew I was always going to move counterclockwise or clockwise around the square there. It would make it a lot easier for my receiving machine to decide which corner of the square that my air link had arrived at, and then generate the appropriate combination of zeros and ones. So this is called, for lack of being very precise, and I'm sure some of the really advanced modulator guys are out there going, "Oh, it's imprecise, it's oversimplified, it's not really that way." Basically, go talk to them. Okay, they'll tell you a week at a time. You'll get the full meal there. But basically, the predictive coding, and one of the most common forms, and popular forms, is called Viterbi, Viterbi, encoding for the guy that invented it. And it says, I'm going to take the data that you give me, whether it's email or audio or whatever, and I'm going to look at that data, and I'm going to generate a sequence of things that I'm going to transmit, a sequence of symbols that I'm going to transmit. But we're all going to know that there's a certain sequence that we're going to take through this constellation pattern. And maybe I have 4 points, maybe I have 8 points, maybe I have 16 points, whatever. There is a certain set of rules that I'm going to apply about how I move around within that constellation. And I know that if I'm here, for example, I'm only going to go like over here somewhere. So if my receiver says, oh, I think he's down here, or he's over here, then I know that's wrong. So that's an error. And by using these codes, I can effectively increase my signal to noise ratio. And when you increase your signal to noise ratio, you can do it by increasing the signal, or you can do it by reducing the noise. And what is noise? Noise is decoding errors. And so if I reduce the number of possibilities that my receiver has to sort through to make a decision, then I can effectively reduce the noise and raise my signal to noise level. So by using these predictive codings, I can raise the number of bits per second that I can pack through my limited amount of bandwidth. Okay, so what do if you detect an error? Well, the next layer up the stack, the next part of what your protocol machine has to do is it has to decide. When you pick a protocol, is the protocol only able to detect an error? If so, it says, can you please send me that data again? And so you get what's called an ARQ or an ACK-NAC, where you have acknowledge and not acknowledge. And it say, I didn't get that last one, send it again. And I'm going to send it, and I'm going to send it until it goes, okay, I got it, ACK, go on to the next one. That's an ACK-NAC or ARQ protocol. But I can also, if I have enough channel capacity, if I have enough signal to noise ratio, I can pack in some redundant data so that the system on the other end can recover from a certain level of errors that occur during transmission, as measured by the bit error rate, which is the number of errors in bits transmitted per second. The higher the bit error rate, the harder it is for me to recover this information. So by using this forward error correction and sending the redundant information along with the data, at the other end, my machine can go, well, I missed this bit, I missed that bit, but I have this little table over here, and I can use this table to fill in. So this bits that I missed must be a 0 over here and a 1 over here, and that's grossly oversimplifying it. But basically, if I've got enough computing power on each end, I can use this predictive coding and these error correction techniques to recover from certain number of errors. And what's happening when you see, for example, on an HD TV signal, when it starts to block or pixelate, is that the machine on the other end is getting so many errors that it cannot recover the real information. It can't fill in, it can't guess, it can't. It's got too many errors to recover from, and so it just throws up blocks or blue screen, or at some point you see the picture break up entirely because the machine on the other end is getting so many errors that it's overwhelmed the error coding, and it throws up its hands and it says, "That's it, signal is low, you're out." And these codes are very powerful. They can maintain a real high quality signal recovery until all of a sudden they can't. And so they just fall off the edge of the table. Whereas with analog, those of you that remember in the old days, let's see, where's my hand over here? You would drive around and listen to FM, and it would get kind of noisier and noisier and noisier and noisier, but you could still, still hear the Beatles or, whatever it was. And then at some point it was just too scratchy and you change the channel. So it was kind of a graceful degradation. But with digital, it's basically just all the way, it's really good, and then all of a sudden it's really not. And so it just falls off the table there. But what you need to do is, after you understand the very basics of the modulation, is start moving up to see how the data is encoded, and then the error management structure of the protocol, and then how does the protocol actually package the data. Some protocols pack audio and video together, plus control, plus information, meta information about the channel. They identify the station and various other things. And then at some point, the protocol takes that apart, takes all that other stuff away, and it generates the audio signal or the video signal that goes to your monitor, your earphones. So start simple, understand one simple set of modulation, and then trace that all the way up to where it shows up at the top as music or picture or email or whatever. And then you'll be well equipped to change and say, well, I can't get my signal through this fast enough, or I need a more robust communication link. Well, then you can start looking at different types of modulation down at the bottom to see the effect, and you'll understand how the effect of that modulation affects everything all the way up to what's called your application level, or the software that you're running on the top. Back to you.
Wow. I'm gonna have to ask Chris Tobin if he's got any last questions, because we're about out of time, I'm told, and that's about as much as I can possibly digest. I got so many more questions, but I got a feeling they take 3 more hours to answer. Chris, what do you got for us?
First of all, with the Viterbi bit error rate, those of you in the audience who remember the Starguide satellite delivery system for network radio, the Viterbi bit rate was 2/3. That was something you had to remember on the receivers. So that was when I managed uplinks, the Earth stations, we had to remember all these little details. And then as far as quadrature amplitude modulation, remember the compatible version of that was called CQAM. So you remember AM stereo. AM stereo was a signal that had a quadrature of 90 degrees and a in phase. And when those two didn't properly match or decode, what did you get? Oh, we got that platform motion effect as I'm moving left to right in the camera right now.
Yes,
so,
yeah.
Those are the things I'm adding in. And then just for giggles and grins, I have here a Motorola APCO 25 compatible radio, which is another form of digital communications to throw into the mix of things we're talking about.
Those of you who have heard my story, I've told many times in public gatherings, this here digital's the coming thing. It's everywhere. Ward, I wish we had another 2 hours, but we don't. And I appreciate so much the time that you've taken to come talk to us about the digital transmission and modulation this evening. Thank you.
You invited me. Thanks. I had to oversimplify things so dramatically. But, go out and start at the bottom, work your way up. If you've got a ham license, you can tinker with this stuff. You can, put your probes down in there and see it go. Or just talk to the experts, at your station or your facility and ask them for textbooks and references and dig through it. It's worth it. It's a really amazing technology. There's a lot of layers to it. It's very complicated, but yep, that digital stuff, it's a coming thing. You bet.
We're not ready to go just yet. I do want to tell our listeners and viewers about our third sponsor, and that's Telos and the Zip1 IP broadcast codec. It's the codec that drops JAWS, not audio. It's that good. There are literally hundreds of radio stations using the Zip1 codec every day for studio transmitter links, and there are hundreds and hundreds more that are using them on an as-needed basis for remote broadcasts, for symphony concerts, for ball games, for remote broadcasts from the Ford dealer or from the county fair. The Zip1 IP broadcast codec is really the Swiss Army knife of codecs. It hooks up, of course, to an internet connection, and that can be wireless, that can be Wi-Fi. You can hook it up to something like, say, a Cradle Point travel router and get yourself some 3G or 4G signal. We've demonstrated it that way in foreign countries when, for example, the wired internet had a big firewall on it that couldn't be penetrated like the one in China. But we demonstrated it with an iPhone and Wi-Fi hotspot, and it worked great. We use the Zip1 IP broadcast codec for, as I said, studio transmitter links all over the state of Florida. Just happens to be one place where several broadcasters are doing this with links from the studio to the transmitter site, redundant links as well, and even the Florida Public Radio Emergency Network connecting 15 public radio stations in Florida all together to provide basically play-by-play warnings for hurricanes and other severe weather. They're all connected together by the Zip1 IP codec. It does all the codecs you're going to want, AAC, high-efficiency AAC, and all that, linear PCM. It does MPEG-2, so it's compatible with older devices, so it's just one codec after G722, in fact, and even G711. You can turn it into a SIP device and have it make a phone call or answer a phone call over a SIP protocol. It works with Lucy Live and Lucy Live Lite. It's just in use all over the place. Our radio stations use it, and so do hundreds and hundreds more. Check it out if you would. Go to the website, telos-systems.com. Look for the Zip1. Zip stands for Zephyr IP. You're all familiar with the ubiquitous Zephyr ISDN codec? Well, this is the IP update to that codec. It's the Zip1. And thanks very much to Telos Systems for sponsoring This Week in Radio Tech. All right, Ward, thanks again for being with us on This Week in Radio Tech. I guess, for more information, you said we just barely scratched the surface of some of these subjects. Ham Radio for Dummies, your book, will cover some of this, and the ARRL handbook that you showed on the screen there, the one for 2015. My goodness, that is packed full of deep information, isn't it?
It's if you're used to buying professional literature, you'll be astounded to find out that it only costs $50. 1,300 pages of good, practical, wireless information at all levels. And if you're not a ham radio operator, here's my little ham radio assistant here. If you're not a ham radio operator, ham radio is the most powerful communication service available to the private citizen in the world. If you would like to take your expertise and experiment with technology or use it in public service or just enjoy operating with it, you can definitely do a lot worse than ham radio. It's a going thing. It's a lot of fun.
Ward, thanks again for being with us, and thanks for taking the time to write that book, Ham Radio for Dummies. I need to update my ARRL handbook as well as get Ham Radio for Dummies, so I am ordering both right after the show. I really am going to make it a present to myself. Chris Tobin, thank you for being with us from Manhattan. Appreciate your contributions.
Oh, you're welcome. And for those who are not ham operators, definitely look into it. I can assure you that I've enjoyed some great tinkering and experimentation with some repeater systems and antenna design and signal propagation to figure out a few things. And I've applied those to the days of when RPUs were popular, and I can assure you that it's paid off handsomely. And now with the digital stuff, you can do even more. So it's definitely worth the look-see.
It sure is. Sure is. Thanks a lot, everyone. We're going to go, and our show's been brought to you by the folks at Axia with the Element console, at Lavo with the Crystal Clear virtual console, the Crystal Clear Fusion, and also from the folks at Telos and the Telos Zip 1, like the one right behind me here. I use it to listen to my stations. We'll see you next week on This Week in Radio Tech. Bye-bye, everybody.